Good morning, everybody, and welcome to this talk by Dr. Antonia Tzemanaki. I am Dr. Catherine Blackwell. I'm the head of the Faculty of Engineering's Industrial Liaison Office. There will be an opportunity for question and answers at the end of the talk, so please do submit questions. You'll find the question and answer tab at the bottom of your Zoom screen, and do add those during the talk and at the end. This talk is part of the Faculty Research Showcase event. The purpose of this week-long event is to demonstrate the breadth of research capability we have in the engineering faculty here at Bristol. We want to provide a stimulus for conversation and hopefully future collaborations. Thank you for joining us today, and I hope that you find the session interesting and thought-provoking. I'm now going to hand you over to Antonia, and she's going to talk about anthropomorphism in medical robotics and beyond.
Thank you very much, Catherine. And good morning, everyone. Thank you for joining this talk. So the title for this, as Catherine mentioned, has to do with anthropomorphism. I will talk about it in the context of medical robotics mostly, but I would like also to make some extensions beyond it in perhaps other areas such as extreme environments. So to start with, what does it mean, anthropomorphism? So I suppose the dictionary definition is to attribute human characteristics or behavior to a god, to an animal, or an object, and in my case, to robotics. So I looked at the research that my group has been doing, and I created this sort of word cloud. And as you can see, there's a lot about surgical, robotic, learning, haptic. Haptic basically means the sense of touch, tele-operation, but a lot to do about hand and hand, because the hand, I think, is the best example that we have really about dexterity and about sensing and haptics. So looking at Charles Darwin and Leonardo da Vinci, they were all really passionate about hands and their shape, their structure. And I am also quite, let's say, passionate about them, because I really see that they have a lot of capability and a lot to offer, and we can learn from them as well. But then perhaps we can also use robotics to learn about them a little bit more. So it's interesting that researchers have found connections between our hands, our fingers, to the fin rays of fish. And this is really important, because that just tells us that humans were not always land creatures. This is evidence to our aquatic past. And of course, then you can also then have a look in a philosophical way. Why did we evolve in the way we did? Is it because we had to make tools, use them to progress in a society, or is it a more pessimistic view of the fact that we had to use weapons to fight each other? But in any case, however you see it, a lot of all the scientists and philosophers and even science fiction writers agree that without our hands in the shape and form that we have them now, the humanity wouldn't have progressed past its primeval age. So starting from that and the hands, I also want to show you these two diagrams. So this is what we called homunculi. So on the left side, we have the motor homunculus, and the right side, you have the sensory homunculus. So these are basically a representation of our human bodies in terms of on the right, how much we sense. So we sense with our hands, with our feet, with our tongue, we taste, we feel temperature differences. And on the left side, where it's the motor, it's basically what we usually use to do things, to do the tasks, to move things around. We use also our mouth to do that a lot. We, as animals do as well. So obviously you can see in both of these representations, the hands are quite a major, crucial part of our bodies. And in fact, obviously you can see and you can imagine yourselves how much you use your hands in your everyday life since you were 2 years old or younger, and you were trying to learn how to fit shapes into others. Then you have dexterity in pianists, cooking, surgery, of course, and we of course use them to feel each other, and we use them to really interact with our environment. That obviously then of course has an impact into our mental health and ability. And of course, this is why the reason that this is also important is also why there's a lot of research in creating prosthetics for people with limb differences. And we know that this is really important because we want to develop them more and more. We want to increase their dexterity and their capabilities. So what does anthropomorphism mean in the area of surgical field and surgical robotics? Of course, we're not talking about robots that look like humans. There's not much point in that, apart from perhaps the aesthetic or the shock value. It's more about using the properties of our hands to transfer them into robotics and make robotics then behave perhaps similar to humans. So I want to show you this video, which is shows one of the surgical robotic systems. So you see here that it's not robotic surgery, it's robot assisted surgery. The surgeon is an integral part and is irreplaceable. So this now robot basically has an interface. It has a joystick that the surgeon uses. And this information then is picked up and sent to the surgical instruments, which you could see here. This is basically the robot that has 4 robot arms, at each of which you have a surgical instrument. So what we thought about the system is that it's really expensive. It costs about £2 million to purchase, £500,000 per year to maintain. The instruments cost £2,000 each. They need maintenance, and after 10 times of use, you get to throw them away because of safety issues. So what we thought of it is, how can we improve this? How can we put the attributes of the human hand in the system to basically improve this and to add portability, to add dexterity, to make the system adjustable to fit to any surgeon if they are a woman or a man with smaller hands or bigger hands, and also to improve the fact that you shouldn't spend thousands and thousands of hours trying to train yourself to use something that is very different to your own hand, because the surgical instruments really look pretty much like chopsticks. And this is not the best tool when you want to do very precise movements. So the system we put together, we named it Microangelo, and it basically has a surgical instrument that looks like a 3-finger instrument, a 3-finger hand. So on the right here, you see the concept. So this sort of inflatable dome that you see here is the actual abdomen. So what happens is that the abdomen is inflated. The surgeons are basically pumping CO2 in the abdomen so that it creates some space for the actual surgery to be performed, the surgical tasks. So in this concept, you can see this 3-finger instrument entering the abdomen, then deploying itself, at which point the surgeon then takes control of it. And the surgeon takes control of it using this sort of exoskeleton that you see in the middle of the screen, which is now an adjustable, rigid glove with sensors that can track the motions of your fingers, joints, and generally hand. So based on that concept, I have created a few different exoskeletons with various teams, the University of West of England, as well as the Bristol University. And you can see a few examples of them here. This is ongoing work. We are improving this, and we are extending this also now, not just surgery, but also nuclear environments, as well as space technologies. And what I also want to mention here is the importance of haptic feedback. We are implementing this in terms of adding cables through this sensory exoskeleton, which then gives the opportunity for the cables to basically tense in a way and give you on your hand the sense of resistance. You're trying to grasp something that you shouldn't squeeze too much, the exoskeleton then resists, and you can feel, oh, okay, maybe I shouldn't do that too much because I might damage the structure. So another type of haptics, another type of sense of touch is something that is smaller than just resistance, something that we usually feel with our fingertips. So this sort of tactile sensing, we also wanted to transfer that in sort of the surgery domain. And we looked at how we can look at diagnoses and when you are in structures that you shouldn't damage, how can the system give you a very discrete sense of feedback about your touch? So you can see here in this video, we basically created a small sort of device that has an inflatable little pillow that squeezes your finger up and down with a little actuator, but also inflates and deflates so that it can give you a different sensation of the stiffness of the object that you're touching. And this can be applied, for example, for diagnosis of a tumor. So you can see here we had the virtual environment on the right, and we had different sort of spheres, bigger, smaller, some were harder, some were softer. So this device could actually differentiate between those different objects. And this is basically part of what we call soft robotics. So we made a device that is robotic, but is also soft. The interaction with your hand with a user is through a soft medium. And of course, soft robotics is much bigger than that. It can also just contain only soft structures, but this is, I suppose, a hybrid. So based on this now concept, we are looking at doing a breast examination that is automatic in a way. So you don't actually have to have a doctor do this for you. You can just go to a robot platform that does it for you. So this is a collaboration between various universities in the UK, and it's funded by Cancer Research UK. So I'll play this video to show you a little bit the concept. So you have the user who has booked a slot at this machine, which is now private and enclosed behind doors. Once you're in the booth, you can actually sit down in front of this platform. Then you have the interface between the breast of the patient or the user and the robotic interface you can see here. So now zooming into this, you can see the breast interacting with the sort of scanner or gripper. Now, everything that you can see here, the white part and the black part inside, they're all soft structures. And the reason we want that is because we want it to be compliant, we want it to be comfortable, we want it to be better than the mammograms that we usually now have, and that they are always reported for being very, very painful for the users. So of course, now after this procedure, the user can see their own results, or they can actually contact their surgeon or the doctor and get it from them. So what is really important about this project is that it basically looks at automating the process so that you can have very frequent tests, perhaps every 6 months, so that you can actually compare your results from 6 months before and now. And this way, we are basically targeting breast health instead of detection of abnormalities. We're looking at making sure that you can be empowered and you can monitor your own health doing so. And how do we do that? Okay, so this is now the novelty of the situation here. We are wanting to build our own tactile sensor. So I'll show you 2 examples of this. So on the top left here of the screen, you can see how the usual breast examination is happening. You can either self-examine or you can have a doctor palpate the breast, and that has basically sort of motions where you tap and you palpate vertically on the breast from different angles and different sides. You can also have sliding motions. So what sort of sensors can we use to detect that? And you have to keep in mind that the breast is soft tissue, and therefore you have to interact with it with something equally soft, but also you have to make sure that you can detect abnormalities within this deep into that soft tissue. And this is where the challenge is. So we've made a couple of sensors that can actually look into doing that. So this is work that I have been doing with my PhD student, George Jenkinson. So he has been developing this really nice soft sensor on the bottom left that basically is pneumatic, and as you're pushing against it, the air is pushing some liquid that is further away from the breast, and we can monitor the change. And by doing so, you can see some examples here on the top right. We have some sort of fake tissue that has inside it embedded a little rigid sphere that you can see here being held by the two fingers. So when now this robot and the sensor palpate this fake skin, you can see that here there is a 3D plot where you can actually determine where it is and how big it is, as well as you can estimate the stiffness of that insertion. And we tested it to see what are really the limits of that sensor. And you can see that we 3D printed some little tiny objects. The smallest of it has a thickness of just 0.6 millimeters. So this is below 1 millimeter, right? And it can still, you can see on the middle here that the system can actually locate them and identify them very, very accurately. So this was one sensor. The other sensor that I'm showing you here works in a similar fashion, but uses different technologies. So it uses a camera, which monitors these sort of white dots that are inside the sensor. This is not something exactly new, and it's not an innovation I have created. There have been a lot of different sensors like this. One of the major ones we are using in University of Bristol is called TACTIP, developed by, developed at the moment by Professor Lepora. But what we really did, and it was an innovation here, is that we added pneumatics. We added basically air, similar to the device I showed you before. So by doing so, we can now adjust the stiffness of the sensor. And by doing so, we can then try to detect different objects of different stiffness. In fact, by also even when they are really deep embedded in tissue. So we're not just looking now at surface of the breast, we're looking inside deep into it. So what is it that holds, the sensors? What is that gripper looking like? So I showed you in the animation concept video before some sort of 3D gripper, and here you can see where the inspiration for that came. So these are drawings that were made by my master student, Sarah Hiyachi. So she took inspiration from a lotus flower and she created this, which of course then we tried to then use in computer-aided design, and we printed something that starts with inspiration, but then of course develops it. And now you see here on the right and how this is actuated. Everything here is soft. So the structures are compliant, they're meant to be comfortable, and they're meant to be also safe interacting with soft tissues such as the breast. So moving on to now how all of this can also be used in different areas. I'm also very interested in rehabilitation and assisting people with either stroke or injuries. So what happens usually when you have a stroke is that half of your body is paralyzed for at least an amount of time. And when that happens, you cannot move one side. And when that happens, that means that you usually don't use this side of your body, which then leads to your joints becoming stiff, becoming even swollen. And when that signal brain to motor function is restored, you still are in pain and you cannot move as well as before because you have lost some of your range of motion. So based on that, and talking again about sort of soft robotics, we have been looking at developing soft gloves that can help you not only rehabilitate, not only exercising, but also perhaps help you with the activities of your daily life. So they can help you perhaps pick up objects that you usually do when you're cooking. So you can see here, this is a work I did with my master students a couple of years ago. So we developed this soft glove that can be made of leather or silicone, and it's basically operated through cables again that can move your hands for you, can move your fingers for you. And this again can be used for exercising, improving your range of motion, maintaining it if you like, or simply help you do motions such as picking up something, and basically again empowering you to make sure that you don't need assistance for all your daily activities. So now this is the last project I'll show you today, and this is about how we can use all these technologies to have societal impact beyond perhaps surgery and medical robotics. So this is a project I'm very passionate about, and you can see here that we have basically developed a system for the recognition of the British Sign Language alphabet, which is of course just the start, because what we really want to be looking at is how we can actually help people learn the sign language and use it in their daily lives. So for that, we have developed this hand tracking device with simple sensors around the fingers, and you can see that you can actually replicate what their hands are doing in simulation. So it was quite an interesting project because it really opens up a lot of pathways on how you can use this further into engaging with the deaf community, learning from them, but of course, again, also introducing this to hearing people that perhaps would want to learn the sign language, or would want to have a little bit an idea about it. So I want to go back to this now from the beginning of my presentation and remind you how hands are important for our dexterity, for our daily lives. And the argument here is that being able to communicate using sign language is an extra ability, an extra power, really, I would say, that a lot of us who do not know of it are missing out on. And so this is basically the goal of this project. And with that, I would like to thank you, and of course, thank you a lot of my researchers working on all these projects that I showed. And with that, I'll pass back to you, Catherine.
Tonia, thank you very much for that talk. Really, really interesting set of projects there that you gave an overview of. My first question for you today is, how do you think that the medical profession is going to respond to this increased use of robotics in healthcare?
Well, that's an interesting question for sure. And the thing is also the question that is a lot in our minds these months with a pandemic, isn't it? So we have seen for the past 12 months a huge push on that domain, and there's quite a lot of funding and a lot of effort from scientists on that. And we have seen that, for example, with COVID, we have seen that robots have been able to really help in hospitals. They have helped with cleaning, they have helped with delivering medicine, they have also helped with communication, and of course there's a lot of help that can be offered in terms of mental well-being and even keeping someone company. So to answer your question, I think that the health profession is actually responding really well to this, and this is because what is certain and what is commonly accepted nowadays, at least, is that robots are not there to replace any of the health professionals. They are there only to improve their life, to help them to do their job better, more efficiently and safely.
Great, thank you. Just a reminder that if you want to ask Tonia a question, then do add your questions and questions in the tab at the bottom of the page. The next question is, how much of your research is bio-inspired?
Well, how much? Quite a lot of it. I suppose just from the fact that my research is surrounded around hands and human hands, that's already bio-inspiration there. What I mentioned in my talk that I didn't really go very far into it is that I have learned about hands through robotics. So one of my exoskeletons, we used it to track the motion of people's fingers, and what sort of how do your joints behave with regards to each other? when you're trying to grasp something, do they all follow some sort of predetermined trajectory? How does it work? When we then build robot grippers, robot hands that replicating your motion, so such as robot prosthetics, hand prosthetics, how do we build them? Do we have just one finger that it has one motor and just does that? Or do we have more detail? And what we learned from my research a few years ago was that you train your hands. So when you're actually moving something like that, just not any specific motion, the finger joints are not really connected. There's not much correlation between them. But when you are grasping something, when you're pinching something, there is more correlation between them. And of course, this really depends on how much you're using your hands and your manually. If you're a pianist, if you're doing really manual work and precision work. So I'm not sure I answered your question anymore, actually. I forgot what it was.
The question was about being bio-inspired, and it
yes,
sounds like you have been very inspired.
It is, and the most recent project was the one about the lotus flower gripper that was again inspired by nature, of course, and by flowers.
Great, thank you. You obviously talked a lot about the medical applications of your research. Do you think there are other areas that it could be used in as well?
Yes, definitely. So we have seen that the surgical tele-operation has basically the same requirements and same sort of setups with the oil industry, with nuclear industry, with space technologies as well. So we're having a project now that we're working on. It's kind of a new project, less than a year old, with Thales Space, and we are looking at the Mars sample return. So how do you take these rocks from Mars and you put them in sort of contained environments? You want to make sure that they don't cross-contaminate, and you still want to manipulate them in an accurate and dexterous way. So putting your hand through a glove and using them inside a glove box is not exactly the most efficient way of doing that. So this now expertise in tele-operation, in dexterity, in haptics, and learning from the human hand can really benefit these industries as well.
And then going back to the medical sector, when do you hope this technology might be used routinely in hospitals?
That's a good question. It's a difficult one to answer. When so you start doing some research, you get involved with companies. Companies hopefully take it forward, and you just basically need a huge amount of funding, and it's not as quick as you would like. So you can take an example of the surgical robotics. For this to be a reality, it started as military projects, and then they didn't actually use it for the military eventually, but then it went to the surgical domain. And it became a huge company that pretty much the entire world is using. But on the positive side, we have seen that, if there is will and funding, things can happen. A very good example is the COVID vaccinations that obviously are now deployed, and that moved so much forward with all the necessary, of course, tests, but also how robotics have been used in the pandemic and have been employed in hospitals in such a short amount of time. So I'm generally positive and optimistic about this being improved and this pipeline actually being shortened.
Thank you. Our next question is a bit different. It's from a recent MA design graduate. So how does one get involved with researchers and engineers to develop ideas and practical solutions for the fantastic research that's being done?
Well, I suppose there are many different ways to do that. Usually you can contact people directly. That's always something that's interesting. You can have chats. I mean, I usually have chats about crazy ideas and blue sky research with lots of different people that are completely outside my area. We also have at the robotics lab. So part of my work is at the Bristol Robotics Lab. And we are actually running a Bristol Robotics Lab conference day on the 30th of June. So there are going to be some opportunity for interaction there as well. But generally, I would say just give us a shout. It's always really welcome. And if it's not me who is the person for you, I can always signpost you to someone else.
That's great, thank you. The last project that you spoke about, your hand tracking research, was a bit different from the other research that you presented. What impact do you think that hand research might have in the future, maybe within schools?
Yeah, that is a dream, really. This is the dream to this is about societal impact. The entire project, it's about engaging with the deaf community, learning from them, including them in our research. So this is about participatory design, and it's about eventually looking at the UK curriculum in schools. How can we now embed this as one of the sort of standard classes that I have? Perhaps in some schools have French classes, English classes. Why not sign language? It's really, really embedded in our culture, and it can benefit us, and it can really benefit the deaf community as well, because we have so much to learn from them, and it's very possible that a lot of them are being ignored at the moment. And we have seen also there was a campaign that was run, and it was called "Where is the Interpreter?" In all these Zoom meetings, in all of the government announcements about the next steps with the pandemic, where was the interpreter? There often wasn't there one. But if this was a bit, we have to raise awareness for this, and we have to extend all of this more. And then I think the impact could be absolutely huge. And I think that the UK could be a really shining star in the entire world in that domain.
Great, thank you. Just to follow up on that question about how to get in touch with people, we will be following up with all of the people who've joined the webinars as part of the showcase this week, and providing contact details for the Industrial Liaison Office, and we can then put you in touch with the speakers and who else might be relevant to speak to. So you will have contact details available to you at the end of the week. Tonia, thank you very much for your presentation. I've just got one final question for you, unless any crop up whilst I'm asking this question. Where do you hope your research may have taken you in 5 years' time?
Oh, that is a question. I don't really know, but I'm hoping that it will take me to a place that I will be able to collaborate with lots of people outside of engineering necessarily and robotics, and create a portfolio of projects that have really close relationship with industry and with societal needs. So this is really, I think, the goal. And the areas that I'm really interested is to just improve interaction between people, improve interaction between people and their jobs, and generally, as I said, the dream is just to improve efficiency and effectiveness and the experience of the users.
Thank you, and that really came across in your presentation, the research that you were doing and the ideas that you've worked on are really inspiring. It's really encouraging to see how things are moving forward to do things differently, particularly within the healthcare sector. And as you say, with the pandemic, things have changed so quickly. We do need new ways of doing things. So yeah, it's great to see that these things are in the pipeline. Yeah. So if there are no further questions that the attendees would like to ask, I'll bring this session to a close. Many thanks for attending and for your questions. And thanks also to you, Tonia, for your presentation.
Thank you for having me.
Obviously, in the current climate, we talked about the pandemic, and unfortunately, online is really the only way that we're able to showcase our research at the moment. And we appreciate that this is not as interactive as we would like, and it doesn't allow the conversations that we would otherwise have usually in our physical showcase events. But if what you've heard today or throughout the week has captured your interest, then please do get in touch with us. The Industrial Liaison Office that I head is here to connect you with students and academics in the Faculty of Engineering. And as I said earlier, we will be sending out our contact details to you after the event so that you can follow up with us. Once again, very much great thanks to you, Tonia, for your presentation, and thank you for joining us. Hope you have a good rest of the week, and goodbye.
Bye, everyone.